Imagine a spaceship could fly at the speed of light. You could reach Mars in a single moment. But here comes the cold truth of the universe. This speed is absolutely unattainable. And when you learn why, your understanding of physics will change completely. Einstein showed more than 100 years ago. The faster you accelerate an object, the heavier it becomes. Near the speed of light, its mass multiplies. At 99%, a spaceship would be 7 times heavier. And at light speed, infinite mass, infinite energy. Completely impossible. Now ask yourselves the following. If the universe has set us a speed limit, how are we ever supposed to reach the stars? The answer is coming. And when you hear it, you will have only one thought. Maybe what we consider impossible isn't so impossible after all. If these cosmic journeys fascinate you every night, don't forget to subscribe to our channel and like the video. This helps the video reach even more people. Thank you in advance. Ready? Then let's begin. Part 1. Warp propulsion. The impossible dream becomes reality. From supersonic jets to lightspeed dreams. Picture this. You're sipping coffee in New York, and 3.5 hours later, you're strolling through Paris. That was the Concorde's promise. A supersonic marvel that shattered what we thought possible in aviation, flying at twice the speed of sound. This engineering masterpiece represented humanity's relentless pursuit of speed. But here's the thing that's nothing compared to what scientists are cooking up right now. We're talking about spacecraft that don't just break the sound barrier. They don't just approach light speed. They exceed it by a factor of 10. Sound impossible. That's exactly what they said about breaking the sound barrier back in 1947. Yet here we are, standing on the precipice of something far more revolutionary. The Concorde is history now, relegated to museums and nostalgic documentaries. Today, only military fighter jets routinely pierce the sound barrier. But humanity? We've moved on to a far bigger challenge, conquering the cosmic speed limit itself. Think about it. What good is reaching Mars in 6 months when the universe sprawls across billions of light years? The nearest star system, Proxima Centauri, sits roughly 4 light years away. With our current technology, that's a journey spanning tens of thousands of years. Your great-grandchildren single quotes as descendants might arrive, but you, not a chance. The distances in space aren't just big, they're mind-crushingly, soul-destroyingly vast. Without faster-than-light travel, we're trapped in our cosmic neighborhood, like prisoners in an open-air jail. But what if I told you scientists have cracked the code? What if the very fabric of space and time could bend to our will, allowing us to leap across the cosmos in the blink of an eye? Stick around, because what comes next will blow your mind. Einstein's iron cage, and how to break free. For over a century, Albert Einstein's equations have been the gospel of physics. His special and general theories of relativity established what seemed like an unbreakable cosmic speed limit. The speed of light, roughly 186,000 miles per second. According to Einstein, nothing with mass can reach that velocity. The reason? Energy. Here's where it gets weird. As an object accelerates closer to light speed, its mass increases. Not metaphorically, literally. The faster you go, the heavier you become, and heavier objects require more energy to accelerate further. By the time you approach light speed, your mass approaches infinity, and accelerating infinite mass, that requires infinite energy. Game over, right? For decades, physicists scratched their heads over this puzzle. How do you explore a universe where the nearest interesting destinations require centuries or millennia to reach? How do you build a civilization among the stars when you're shackled by the laws of physics themselves? Einstein's equations were beautiful, elegant, and maddeningly restrictive. They seemed to doom humanity to an eternity as cosmic shut-ins, forever gazing at stars we could never touch. But here's where human ingenuity comes into play. Instead of fighting Einstein's laws head-on, scientists asked a different question. What if we could sidestep them entirely? What if, instead of pushing a spacecraft to light speed, we could manipulate the space around it? That's not cheating, it's creative problem-solving. And it might just be the key to unlocking the universe. The breakthrough came from an unexpected place: science fiction. For decades, stories about warp drives captured imaginations worldwide. From the Starship Enterprise zipping across the galaxy to countless other fictional vessels, the concept was irresistible. But could imagination become reality? Could we actually warp space itself? The birth of warp drive, science fiction meets science fact. Let's talk about warp drive. If you've ever watched a science fiction movie, you know the drill. The spaceship revs up, there's a flash of light, and suddenly it's millions of miles away. The Enterprise could travel 9,000 times faster than light at maximum warp. Distances that should take centuries vanish in moments. It's exhilarating, inspiring, and until recently purely fictional. But science fiction has this uncanny habit of becoming science fact. Authors like John W. Campbell and the legendary Gene Roddenberry weren't just entertaining us. They were planting seeds. They made us dream. They made us wonder, why not? And eventually, scientists started asking the same question. In the 1990s, physicists began seriously exploring warp drive concepts. The key insight: Einstein's equations don't prohibit warping space itself, only moving through space faster than light. See the difference? Instead of accelerating a spacecraft using conventional thrust, what if we compressed the space in front of the ship and expanded it behind? The ship wouldn't technically move through space at all. Space would move around the ship. It's like surfing a wave instead of swimming through water. The wave does the work. This isn't just clever wordplay. It's a genuine loophole in the laws of physics. Einstein's special relativity says objects can't exceed light speed when moving through space. But general relativity, Einstein's theory of gravity and spacetimes, says space itself can expand or contract at any speed. In fact, space does this all the time. During the Big Bang, space expanded faster than light. It's still expanding today, carrying distant galaxies away from us at incredible velocities. If space can move that fast naturally, why can't we harness that phenomenon artificially? The answer is energy. Warping space requires power, lots of it. Early calculations suggested you'd need the energy equivalent of the entire planet. Jupiter converted into pure energy just to create a small warp bubble. That's roughly 1.9 trillion kilograms of mass transformed into energy via Einstein's famous equation. E equals mc squared. Not exactly practical for your average Tuesday afternoon commute. But here's where things get interesting. What if we've been thinking about this problem all wrong? What if the energy requirements aren't as astronomical as we thought? What if there's a trick we're missing? Miguel Alcubierre's revolutionary breakthrough. Enter Miguel Alcubierre, a Mexican physicist who changed everything in 1994. While working on his doctoral thesis at the University of Wales, Alcubierre did something remarkable. He used Einstein's own equations, the same ones that seemed to forbid faster than light travel, to prove that warp drive could actually work, theoretically at least. Alcubierre's insight was brilliant in its simplicity. He proposed creating a warp bubble around a spacecraft. Within this bubble, space-time would contract in front of the ship and expand behind it. The ship itself wouldn't move through space at all, it would ride a wave of warped space-time, like a surfer catching a perfect swell. From the perspective of someone outside the bubble, the ship would appear to move faster than light. But from the perspective of the crew inside, they'd be sitting still, sipping coffee, completely unaware of their incredible velocity. Think about it this way. Imagine you're standing on a long carpet. Walking from one end to the other takes time and effort. But what if someone bunched up the carpet in front of you and stretched it out behind you? Suddenly, the far end is right at your feet. You didn't walk any faster, you just shortened the distance. That's essentially what the Alcubierre drive does with space-time itself. The mathematics checked out. The physics were sound. There was just one tiny problem, that pesky energy requirement. Alcubierre's original calculations suggested you'd need negative energy, also called exotic matter, to create the warp bubble. And here's the kicker. Negative energy had never been observed in nature. It was purely theoretical. Building a warp drive with negative energy was like being told you could fly to Mars if you just found some unicorn tears for fuel. Theoretically possible, practically useless. But Alcubierre had opened a door. He'd proven that faster-than-light travel didn't violate the laws of physics. It was allowed, as long as you could solve the energy problem. And when scientists know something is possible in principle, they get motivated. Very motivated. The mechanics of the impossible. Let's dig deeper into how an Alcubierre drive would actually work, because this is where things get truly mind-bending. The key concept is the warp bubble, a region of distorted space-time surrounding the spacecraft. Inside this bubble, space remains flat and normal. The laws of physics work exactly as expected. The crew wouldn't feel any acceleration or weird forces. They could walk around, eat lunch, maybe play some cards. Just another day at the office. But outside the bubble, that's where the magic happens. In front of the ship, space-time contracts. Distances shrink. A light year might compress down to a single mile. Behind the ship, space-time expands. A mile stretches into a light. The bubble itself then surfs along the boundary between these compressed and expanded regions, carrying the ship along for the ride. Here's the brilliant part. The ship never accelerates. It never pushes against anything. It just sits there while the universe rearranges itself around it. This neatly sidesteps Einstein's prohibition against faster-than-light travel. The ship isn't moving faster than light through space. Space itself is moving, carrying the ship along. It's the ultimate cosmic free ride. Now, you might be wondering, what would this look like from the crew's perspective? Surprisingly normal, actually. Remember, inside the bubble, space-time is flat and understood. You wouldn't feel squished or stretched. You wouldn't experience crushing g-forces or time dilation. You might notice a slight vibration, maybe see stars streaking past in elongated trails of light, but otherwise, it would be like sitting in a really smooth car on a really straight highway. Compare that to conventional rocket propulsion. Accelerating to even a fraction of light speed would subject astronauts to enormous forces. Their bodies would be pressed into their seats with crushing weight. Time would dilate, meaning a few years aboard ship might equal decades back on Earth. The psychological and physical toll would be immense, but warp drive bypasses all of that. It's gentler, safer, and infinitely more practical for long-distance space travel. Of course, there's still that energy problem. Alcubierre's original design required exotic matter with negative energy density. What does that even mean? In physics, most things have positive energy and positive mass. A rock has mass. A photon has energy. These are normal, everyday quantities. But negative energy, that's something entirely different. It would have to push instead of pull, repel instead of attract. It would behave opposite to everything we know about matter and energy. Does negative energy exist? Maybe physicists have observed something called the Casimir effect, where two metal plates placed incredibly close together in a vacuum experience a tiny attractive force. Some interpretations suggest this force involves negative energy fluctuations in the quantum vacuum, but we're talking about minuscule effects on a nanoscopic scale, not nearly enough to power a spacecraft. So for years, the Alcubierre drive remained a beautiful mathematical idea with no practical path to realization. Scientists could prove it worked on paper, but building one seemed as impossible as ever. The dream of warp drive appeared destined to remain forever locked in the realm of science fiction. But then, something unexpected happened. Multiple breakthroughs, arriving from different directions, began to change the game entirely. The energy crisis solved. Fast forward to 2010. Dr. Harold Sonny White, working at NASA's Johnson Space Center, began revisiting the warp drive concept with fresh eyes. White wasn't content to accept defeat. He wondered, could we reduce the energy requirements? Could we make warp drive practical? What White discovered was revolutionary. By tweaking the shape and configuration of the warp bubble, he found he could dramatically reduce the energy needed, instead of requiring the mass energy equivalent of Jupiter. White's refined design needed only about the mass of a large spacecraft, roughly 1,600 pounds. That's still a lot of energy, mind you. Converting 1,600 pounds of matter into pure energy would unleash a staggering amount of power. But it's not impossible. It's not ridiculous. It's in the realm of future engineering possibility. White's optimization relied on making the warp bubble thicker and adjusting its geometry. Think of it like this. If Alcubierre's bubble was a thin soap bubble, White's was more like a thick-walled balloon. This changed how space-time distorted around the ship, requiring less exotic matter to maintain the warp field. It was still theoretical, still dependent on negative energy, but suddenly warp drive seemed closer to achievable. But the real bombshell came in 2021. White, along with several colleagues, published a paper describing something extraordinary. They'd accidentally discovered a real warp bubble working on an entirely different project involving the Casimir effect. White noticed tiny structures forming between metal plates in a vacuum. These structures exhibited all the mathematical signatures of miniature warp bubbles. They were natural, spontaneous, and absolutely real. Let that sink in for a moment. Warp bubbles aren't just theoretical constructs. They exist in nature, forming spontaneously at microscopic scales. If we can understand how they form and learn to scale them up, we might be able to create artificial warp bubbles large enough to enclose a spacecraft. This isn't speculation anymore, it's engineering. The Defense Advanced Research Projects Agency DARPA, the military's Mad Science Division, immediately took notice. They began funding further research into warp bubble mechanics. When DARPA gets interested, you know something big is brewing. They don't waste money on pipe dreams. They invest in technologies that could actually work within the next few decades. The soliton solution, riding the wave. Meanwhile, another physicist was approaching the problem from a completely different angle. Dr. Eric Lentz at the University of Göttingen proposed something that sounded too good to be true. a warp drive that doesn't require negative energy at all. Lentz's breakthrough came from studying soliton stable wave packets that maintain their shape while moving through a medium. Think of ocean waves rolling toward shore. Most waves break and disperse, losing energy and form. But solitons are special. They're self-reinforcing, stable, and can travel vast distances without falling apart. Lentz realized that space-time itself could support soliton-like structures, warp bubbles made from ordinary positive energy. His design uses carefully configured shells of positive energy density to create a warp effect. No exotic matter required. No negative energy needed. Just extremely high concentrations of positive energy arranged in specific geometric patterns. It's like building a bridge with conventional materials instead of needing some impossible wonder material. Now, before you get too excited, Lentz's design still requires enormous amounts of energy. We're talking about power outputs equivalent to the total energy consumption of a major nation over several years, all focused into a volume smaller than a house. That's beyond our current engineering capabilities, but it's not impossible in principle. Future fusion reactors or antimatter engines might be able to generate that kind of power. And critically, it doesn't require anything we know to be impossible. Just really, really difficult. The implications are staggering. If Lentz is right, warp drive technology could be achievable with conventional physics and engineering. No need to hunt for exotic matter or figure out how to stabilize negative energy. Just extremely advanced but theoretically buildable technology. It shifts warp drive from probably impossible to difficult but doable, and that changes everything. Think about what this means. Within perhaps a century, maybe less, humanity could possess the ability to travel between stars in days or weeks instead of millennia. Alpha Centauri, our nearest stellar neighbor, could become a weekend trip. The entire Milky Way galaxy could open up to exploration and colonization. We'd go from being imprisoned in our solar system to being free citizens of the cosmos. The dream that seemed forever out of reach is suddenly tantalizingly close. Where we are now, the painful truth. But let's pump the brakes for a moment and face reality. As exciting as these breakthroughs are, we're still not there yet. Not even close. To understand just how far we have to go, let's look at where we actually stand right now with space travel technology. Our fastest spacecraft ever built is the Parker Solar Probe, which reached velocities up to 119 miles per second near the Sun. That sounds incredibly fast, and it is, by human standards. But in cosmic terms, it's barely moving. At that speed, Parker would take over 6,500 years to reach Proxima Centauri. That's older than recorded human history. The pyramids would be ancient by the time it arrived. Voyager 1, launched in 1977, is humanity's most distant spacecraft. After nearly 50 years of travel, it's finally left the solar system, now more than 14 billion miles from Earth. It's moving at about 11 miles per second. At that rate, Voyager would need roughly 75,000 years to reach Proxima Centauri. Your distant ancestors were just figuring out how to use stone tools when that journey would have begun. See the problem? Even our most advanced spacecraft are ludicrously slow on cosmic scales. We can barely escape our own solar system, let alone venture to other stars. And these probes are tiny, just hundreds of pounds of instruments and equipment. Scaling up to a crude spacecraft that could sustain human life for years or decades would require even more energy and resources. This is why scientists use gravity-assist slingshotting spacecraft around planets to gain speed without burning extra fuel. The Juno probe, which studied Jupiter from 1995 to 2003, used multiple gravity assists to reach speeds of about 46 miles per second, still nowhere near light speed, which is 186,000 miles per second. We're not even in the same ballpark. We're not even playing the same sport. And here's the really depressing part. Even if we could reach a significant fraction of light speed, say 10%, the journey to Proxima Centauri would still take 40+ years, a human lifetime. You might depart as a young astronaut and arrive as an elderly one, assuming you survived the journey at all. Your family and friends back on Earth would age alongside you, their lives progressing while you hurtled through the void. It's not exactly the inspiring vision of space exploration we've been sold. This is why warp drive isn't just a cool idea, it's a necessity. Without it, interstellar travel remains a fantasy. With it, the galaxy becomes our playground. The difference between those two scenarios is the difference between humanity remaining forever trapped on one world versus becoming a true spacefaring civilization spanning thousands of planets. It's not hyperbole to say that warp drive technology could be the most important development in human history, and we're closer now than ever before. So where does that leave us? Stuck between an impossible dream and inevitable reality. The physics says warp drive is possible. The engineering says we're decades, maybe generations away from building one. But every year, scientists make new discoveries. Every year, our understanding deepens. And every year, the dream gets a little bit closer to real. The question isn't if we'll develop warp drive, it's when, and whether we'll be ready for the universe that awaits us when we finally break free from Einstein's cage and step out into the infinite cosmos beyond. The adventure is just beginning, and what comes next will reshape everything we think we know about reality itself. Are you ready? Part 2. Current space technology. Why we're still crawling. The harsh reality of our cosmic speed limit. Let's get brutally honest for a moment. While scientists dream about warp drives and faster-than-light travel, we're still struggling with the basics. Our current spacecraft move through space at speeds that would embarrass a cosmic snail. The gap between where we are and where we need to be isn't just large, it's almost comically vast. But understanding this gap is crucial, because it shows us exactly why breakthrough technologies like warp drive aren't just convenient, they're absolutely essential for humanity's survival as a spacefaring species. The Juno spacecraft, which orbited Jupiter and gave us stunning insights into the gas giant's mysteries, represents some of our best work. Launched with tremendous fanfare and cutting-edge technology, Juno reached impressive speeds by human standards, about 46 miles per second during certain phases of its mission. That's fast enough to cross the United States in less than a minute. Sounds incredible, right? But here's the gut punch. At that velocity, Juno is traveling at roughly 0.0025 times the speed of light. Not 25%, not even 0.25%. We're talking about 0.02% of light speed. Put another way, if light were a supersonic jet, Juno would be a toddler crawling across a football field. The comparison isn't even fair, it's depressing. And Juno represents decades of engineering advancement, billions of dollars in investment, and some of the smartest minds on the planet working together. This is the best we can do right now. Think about that for a second. Our pinnacle achievement in space propulsion technology is still pathetically slow on a cosmic scale. Voyager 1 tells an even more sobering story. Launched back in 1977, the same year Star Wars hit theaters, this probe has been traveling for nearly 50 years. It's covered an astonishing 14 billion miles, making it the most distant human-made object in existence. In 2012, it finally crossed into interstellar space. leaving behind the protective bubble of our sun's influence. This was celebrated as a monumental achievement, and rightfully so. Humanity had reached beyond our solar system for the first time in history. But here's what they don't tell you in the press releases. Voyager 1 is moving at roughly 11 miles per second. At that speed, it would take approximately 75,000 years to reach Proxima Centauri, our nearest stellar neighbor. 75,000 years. That's 3 times longer than human civilization has existed. When Voyager 1 finally arrives, it's still functioning. Which it absolutely won't be. Our species might not even exist anymore. We could have evolved into something entirely different, or gone extinct, or transcended physical form entirely. The probe would arrive at a dead star system, a silent witness to a journey that spanned geological epochs. And remember, Voyager is unmanned. It's a tiny spacecraft weighing less than a ton, carrying primitive 1970s technology and powered by decaying plutonium. Now imagine trying to send humans on that same journey. You'd need a massive ship with life support, food, water, radiation, shielding, and space for multiple generations to live, reproduce, and die en route to a destination they'd never see. It's not just impractical, it's borderline insane. The Parker Solar Probe, our speed champion. Let's talk about our current record holder. The Parker Solar Probe. This magnificent piece of engineering represents the absolute cutting edge of space propulsion technology, designed to study the sun's outer atmosphere. Parker uses the sun's own gravity to accelerate to mind-blowing speeds. During its closest approaches, Parker reaches velocities up to 119 miles per second, roughly 430,000 miles per hour. That's fast enough to fly from Los Angeles to Tokyo in less than 20 seconds. By human standards, it's absolutely extraordinary. Parker is the fastest human-made object ever created. Nothing we've built moves faster. Not our rockets. Not our satellites, not our space shuttles. Parker holds the crown, and it's a crown well earned. The engineering required to achieve these speeds, while simultaneously surviving the intense heat and radiation near the sun, represents decades of scientific advancement. The probe's heat shield must withstand temperatures exceeding 2,500 degrees Fahrenheit, while the instruments behind it remain at room temperature. It's a technological marvel, a testament to human ingenuity and determination. But even Parker, our fastest achievement, is laughably slow in cosmic terms. At 119 miles per second, it's traveling at roughly 0.064% of light speed, not 64%-0.0-64%. To put this in perspective, light could lap Parker more than 1,500 times in a single second. If light were running a race, Parker would still be at the starting line when light finished a marathon. At Parker's maximum velocity, a journey to Proxima Centauri would still take approximately 6,500 years. That's longer than recorded human history. The ancient Egyptians were building pyramids 6,500 years ago. If they'd launched Parker back then, it would just now be arriving at our nearest stellar neighbor. By the time it got there, Egypt had risen and fallen, entire civilizations had come and gone, languages had evolved and died, and the whole of human culture had transformed beyond recognition dozens of times over. And this assumes Parker could even survive the journey, which it absolutely couldn't. The probe is designed for a mission lasting several years, not millennia. Its power source would die within decades. Its systems would fail. Cosmic radiation would degrade its electronics. Micrometeorites would slowly sandblast its exterior. By the time it reached Proxima Centauri, It would be nothing but a lifeless hunk of metal drifting through space, a tomb for our ambitions. This is the reality we face. Our fastest spacecraft, the culmination of everything we know about propulsion and engineering, is still grotesquely inadequate for interstellar travel. We're not even close. We're not in the ballpark. We're not playing the same sport. And that's precisely why breakthroughs like warp drive aren't just interesting, they're absolutely critical for humanity's future among the stars. Gravity assists, the cosmic slingshot. Since we can't brute force our way to high speeds, we've gotten creative. Enter the gravity assist, also called a gravitational slingshot, one of the cleverest tricks in the space travel playbook. The concept is elegantly simple. Use a planet's gravity and orbital motion to accelerate a spacecraft without burning any fuel. It's like catching a ride on a cosmic merry-go-round, using the planet's momentum to boost your own velocity. Here's how it works. As a spacecraft approaches a planet, it falls into the planet's gravitational well, gaining speed. If the trajectory is calculated perfectly, the spacecraft whips around the planet and flies out the other side, now traveling much faster than before. From the planet's perspective, the spacecraft gained no net energy, came in fast and left fast. But from the sun's perspective, the spacecraft stole a tiny bit of the planet's orbital momentum, translating into a significant speed boost for the much lighter probe. This technique has become essential for deep space missions. The Voyager probes used gravity assists from Jupiter and Saturn to reach their incredible speeds. The Cassini spacecraft performed multiple flybys of Venus, Earth, and Jupiter to reach Saturn. New Horizons, which flew past Pluto in 2015, used Jupiter's gravity to shave years off its journey time. Without these assists, these missions would have been impossible with current rocket technology. But here's the catch. Gravity assists require careful planning and extraordinary patience. You can't just point your spacecraft at Jupiter and go. You need to wait for the planets to align in specific configurations, which might only happen once every decade or more. Mission planners spend years calculating intricate trajectories, threading spacecraft through narrow orbital windows with precision measured in seconds. A single miscalculation could send your probe careening off into space. Mission failed, billions of dollars wasted, and even with perfect execution, gravity assists only get you so far. The Juno mission to Jupiter used Earth for a gravity boost, taking a circuitous route that added years to the journey. The Europa Clipper mission, launching in the mid-2020s, will take 6 years to reach Jupiter, despite being only about 390 million miles away at closest approach. That's an average speed of roughly 7 miles per second by Earth standards, pathetic by cosmic ones. Imagine if terrestrial travel worked this way. Honey, I'm heading to the store for milk. I'll be back in 6 years. Sigh, need to loop around Antarctica twice and slingshot past Alaska to build up enough speed. It's absurd. Yet this is the state of the art for space travel. We're reduced to playing elaborate orbital billiards, banking spacecraft off planets like trick shots, just to reach destinations within our own solar system. Forget other stars, we can barely manage our own cosmic backyard efficiently. The frustration is real, and it should be. We're living in the 21st century with supercomputers in our pockets and rovers on Mars. Yet, we're still using techniques that would seem primitive to any hypothetical alien civilization. Advanced enough for interstellar travel. Can you imagine explaining gravity assists to beings who routinely travel between star systems? Well, you see, we can't go fast enough. So we throw our spacecraft around planets like cosmic pinballs to steal tiny amounts of momentum. they'd probably laugh themselves into hypoxia. The Proxima Centauri problem, coffee with the cosmic neighbors. Let's paint a picture that really drives home how ridiculously slow our current technology is. Imagine you've got a buddy living in the Proxima Centauri system. He's a great guy, makes excellent coffee, and invites you over for the weekend. "Come on by," he says. "It's only for light years away. We'll catch the game and have some laughs." Sounds great, right? Weekend trip to visit a friend. How hard could it be? With our current spacecraft, technology, specifically something comparable to Voyager 1, the journey would take roughly 75,000 years. 75,000 years for a cup of coffee. By the time you arrived, your friend would be dust. His great-grandchildren's single quotes as civilizations would have risen and fallen. The coffee would be somewhat stale. You might even miss the heat death of a few stars along the way. But wait, you might say, what if we use our fastest spacecraft, the Parker Solar Probe? Great thinking. Parker would cut that journey down to a mere 6,500 years. Still long enough for human civilization to completely transform multiple times over. But hey, at least you'd arrive before the next ice age ends. Your buddy's descendants might still be around. Assuming they kept detailed genealogical records and maintained the family coffee tradition for 200 generations. This isn't just a funny thought experiment, it's a genuine problem that exposes the absolute inadequacy of our current propulsion systems. Proxima Centauri is our nearest stellar neighbor. It's literally the closest star system to our own. If we can't feasibly reach the nearest target, how on earth or off it are we supposed to explore the galaxy? How do we investigate potentially habitable planets orbiting other stars? How do we search for extraterrestrial life, establish off-world colonies, or ensure humanity's long-term survival by spreading across multiple star systems? The answer is, we can't. Not with current technology. Not even close. We're trapped in our solar system as surely as if we were imprisoned on a single island in the middle of an infinite ocean with no boats capable of reaching the next landmass. We can see other islands on the horizon. We've detected thousands of exoplanets orbiting distant stars, but we can't reach them. We're cosmic castaways, marooned by the limitations of our own technology. And it gets worse. Even if we could somehow convince people to embark on multi-generational voyages lasting thousands of years, the logistics would be nightmarish. You'd need a spacecraft large enough to support a sustainable population for hundreds of generations. You'd need closed-loop life support systems that could recycle air, water, and waste indefinitely. You'd need protection from cosmic radiation, which would bombard the ship constantly throughout its journey. You'd need to maintain genetic diversity to prevent inbreeding. You'd need social structures stable enough to last for centuries without collapsing into chaos or civil war. And perhaps most challenging of all, you'd need to preserve the mission's purpose across those many generations. The people who arrive at Proxima Centauri would be hundreds of generations removed from the people who launched. Would they still care about the original mission? Would they still identify as human in any meaningful sense? Would they have any connection whatsoever to Earth, a planet none of them had ever seen, a world that existed only in stories passed down through countless retellings? This is the Proxima Centauri problem in a nutshell. Our nearest stellar neighbor is unreachable with current technology, and even if we could reach it, the journey would be so long and so difficult that it strains the limits of what's possible or sensible. This is why warp drive isn't just a neat idea from science fiction. It's an absolute necessity if humanity is ever going to become an interstellar species. Without faster-than-light travel, we're stuck here forever, gazing wistfully at stars we'll never touch. Human bodies versus space, a losing battle. Let's shift gears and talk about something even more challenging than propulsion. Keeping humans alive during long-duration space missions. Even if we solved the speed problem tomorrow, we'd still face the brutal reality that human bodies were not designed for space travel. We evolved in Earth's gravity well, under its protective magnetic field, breathing its atmosphere. Space wants to kill us in about a dozen different ways simultaneously. Start with the International Space Station, humanity's most ambitious long-term space habitation project to date. Astronauts aboard the ISS typically spend 6 months in orbit before returning to Earth. 6 months. That's the standard mission duration. Why not longer? Because extending beyond 6 months significantly increases the risk of serious, potentially permanent health problems. The human body starts breaking down in microgravity, and the longer you stay, the worse it gets. First, there's muscle atrophy. Without gravity to work against, muscles don't need to work as hard. They weaken and shrink. Astronauts aboard the ISS exercise for 2 hours every single day using specialized equipment, and they still lose muscle mass. After 6 months, they need assistance walking when they first return to Earth. Their legs are simply too weak to support their own body weight. Imagine that half a year in space leaves you temporarily unable to walk. Now imagine a multi-year journey to Mars or beyond. Bone density loss is even more serious. In microgravity, bones don't experience the constant stress they evolved to handle. The body responds by breaking down bone tissue faster than it can rebuild it. Astronauts lose approximately 1 to 2% of their bone mass for every month spent in space. After a year-long mission, you're looking at 12 to 24% bone loss, levels comparable to severe osteoporosis. And unlike muscle, bone density doesn't fully recover when you return to Earth. That loss is largely permanent. Then there's vision problems. Many astronauts return from long-duration missions with degraded eyesight. The cause appears to be fluid shifts in the body. On Earth, gravity pulls fluid downward, away from your head. In space, that fluid redistributes, increasing pressure in the skull and behind the eyeballs. This can flatten the eyeballs slightly and cause structural changes to the optic nerve. Some astronauts need stronger glasses after returning. Others experience permanent vision changes. We don't fully understand the mechanism yet, which makes it even more concerning. And we haven't even mentioned cancer yet. Outside Earth's protective magnetosphere, cosmic radiation bombards everything constantly. High-energy particles from distant stars and galaxies slam through spacecraft walls, through equipment, through human tissue. Every radiation hit risks damaging DNA, potentially causing mutations that lead to cancer. The longer you're in deep space, the more exposure you accumulate, and the higher your cancer risk becomes. Current estimates suggest that a multi-year Mars mission could increase an astronaut's lifetime cancer risk by several percentage points. Significant and sobering number. Psychological factors are equally challenging. The ISS is cramped, noisy, and offers no privacy. Astronauts live in close quarters with the same handful of people for months on end. They can't go outside. They can't escape. They can see Earth through the windows, a beautiful blue marble hanging in the void, but they can't go home. Not yet. Not until their mission ends. The psychological strain is immense, even for individuals specifically selected and trained for these conditions. Now multiply all these problems by a factor of 10 or more for a journey to Mars, which would take 6 to 9 months each way using current propulsion technology. That's over a year in space minimum, possibly closer to 2 years by the time you include surface time on Mars. The crew would arrive weakened, with degraded bones and muscles, possibly impaired vision, elevated cancer risk, and having endured over a year of psychological stress in a tin can hurtling through the void. And then they'd need to perform complex scientific work on the Martian surface before attempting the equally grueling return journey. This is why warp drive and similar breakthrough technologies are so crucial. If we could reduce journey times from months to days or weeks, we'd dramatically reduce radiation exposure, muscle and bone loss, psychological stress, and numerous other health risks. A week-long journey to Mars is vastly different from a 9-month ordeal. Your body barely has time to start adapting to microgravity before you arrive. You're not exposed to months of cosmic radiation. The psychological burden is manageably, basically a long road trip rather than a years-long exile. Without faster propulsion, human space exploration beyond Earth orbit will always be limited, dangerous, and expensive. We might manage a Mars mission or two, perhaps even establish a small research base, but genuinely expanding into the solar system and beyond, not happening. Not with current technology, not without paying an unacceptable price in human health and safety. We need better drives, faster ships, and shorter journey times. The alternative is resigning ourselves to remaining forever bound to Earth, watching the cosmos from afar, but never truly experiencing it. The Mars dream, Elon's gamble. No discussion of humanity's space future would be complete without mentioning Elon Musk and his audacious plans for Mars colonization. Love him or hate him, Musk has done more to reignite public interest in space exploration than anyone since the Apollo program. Through SpaceX, he's developed reusable rockets, drastically reduced launch costs, and made bold promises about establishing a self-sustaining city on Mars within our lifetimes. It's inspiring, ambitious, and according to many experts, wildly optimistic at best and dangerously naive at worst. Musk's vision is seductive. He paints a picture of thousands of people living on Mars, working in bustling cities beneath protective domes, perhaps terraforming the planet over centuries to make it more Earth-like. He talks about making humanity a multiplanetary species, ensuring our survival even if catastrophe befalls Earth. It's stirring stuff, the kind of bold vision that captures imaginations and inspires the next generation of engineers and scientists. But vision and reality are often very different things. The challenges are staggering. First, there's the journey itself. Using current propulsion technology, the trip to Mars takes 6 to 9 months, depending on the orbital alignment of Earth and Mars. That's half a year to a year of the health problems we just discussed: radiation exposure, muscle atrophy, bone density loss, vision problems. And unlike ISS astronauts who can return to Earth in a few hours if there's an emergency, Mars-bound travelers are committed. There's no turning back halfway through. If something goes wrong, medical emergency, equipment failure, psychological breakdown, you're on your own for months until you reach Mars. Then there's Mars itself, which is spectacularly hostile to human life. The atmosphere is 95% carbon dioxide and less than 1% the density of Earth's atmosphere. You can't breathe it. The average temperature is -80 degrees Fahrenheit. Dust storms can envelop the entire planet for months. There's no magnetic field, so surface radiation levels are dangerously high. Perchlorate salts in the soil are toxic to humans. The gravity is only 38% of Earth's, which means long-term residents would likely suffer bone and muscle problems even with exercise regimens. Building a self-sustaining colony under these conditions isn't just difficult, it's monumentally challenging. Every resource would need to be produced locally or shipped from Earth at enormous cost. Water would need to be extracted from ice deposits. Oxygen would need to be generated from the atmosphere. Food would need to be grown in pressurized greenhouses. Manufacturing would need to be developed from scratch, using local materials. Medical care, entertainment, social structures, governance, everything would need to be built from nothing in one of the most hostile environments imaginable. And let's be honest, who's going to volunteer for this? The first Mars colonists would be pioneers in the truest sense, living in cramped habitats, working constantly just to stay alive, cut off from Earth with communication delays of up to 22 minutes each way. No restaurants, no concerts, no beaches, no forests, just red rocks, dust storms, and the constant awareness that a single equipment failure could kill you and everyone you know. It's romantic when you're reading about it in a science fiction novel, less so when you're actually living it, breathing recycled air and eating algae paste while cosmic radiation slowly increases your cancer risk. In 2019, astrophysicist Neil deGrasse Tyson publicly challenged Musk on Twitter, suggesting he should stop focusing on Mars missions and instead invest in developing warp drive technology. Tyson's point was valid. Without faster propulsion, Mars colonization will always be limited, dangerous, and expensive. But Musk's response was equally interesting. He suggested that the drive to establish a Mars colony would actually motivate the development of warp drive and other breakthrough technologies. Who's right? Maybe both of them, maybe neither. Perhaps attempting Mars colonization with current technology is necessary to push us toward the breakthroughs we need. Or perhaps it's a distraction from the fundamental research that could actually make interstellar travel possible. Either way, the debate highlights a crucial tension in modern space exploration. Do we push ahead with incremental improvements to existing technology, or do we hold back and wait for revolutionary breakthroughs? The truth is probably somewhere in the middle. We should absolutely continue pushing the boundaries with missions to Mars and beyond, but we also need to invest heavily in fundamental research, warp drives, advanced propulsion systems, anything that could provide orders of magnitude improvements over chemical rockets. Because at the end of the day, chemical rockets simply aren't good enough. They'll never be good enough. We need something radically better, something that makes the solar system accessible in days or weeks rather than months or years. Without that, Mars remains a distant dream rather than a realistic goal. SpaceX and Blue Origin are doing incredible work pushing the envelope of what's possible with current technology. Reusable rockets are genuinely revolutionary. Reduced launch costs open up possibilities that were economically impossible just a decade ago. But there's only so far current technology can take us. Eventually, we hit fundamental limits imposed by physics and chemistry. To go beyond those limits, we need new physics, new technologies, new ways of thinking about propulsion and space travel. We need breakthroughs, and we need them soon, because the longer we wait, the longer humanity remains trapped in its cradle, never quite growing up enough to leave home and explore the vast universe beyond. The question isn't whether Musk will establish his Mars city in the 2030s or 2040s or ever. The question is whether humanity collectively will commit to the kind of fundamental research and long-term thinking required to make genuine interstellar civilization possible. Because right now, we're not there. We're not even close. And unless something changes dramatically, we might never be. That's the real challenge facing us, not building better rockets, but completely reimagining what space travel could be. and that requires vision, investment, and a willingness to pursue ideas that seem impossible until suddenly they're not. Part 3. Warp Drive Breakthroughs. The Race to Bend Reality. Dr. Harold White's game-changing discovery. Remember that energy problem we talked about? The one requiring Jupiter's mass converted to pure energy? Well, in 2010, Dr. Harold Sonny White at NASA's Johnson Space Center decided that wasn't good enough. White wasn't some fringe scientist working in his garage. This was a NASA physicist with credentials, resources, and most importantly, the audacity to believe warp drive could actually work. And what he discovered changed everything. White took Alcubierre's original equations and started tweaking them. Not random changes, but careful, methodical adjustments based on deep understanding of the underlying physics. He asked a simple question. What if the warp bubble's shape matters more than we thought? What if, by optimizing its geometry, we could drastically reduce energy requirements? Turns out, he was right. By making the bubble thicker and adjusting its configuration, White's refined design dropped the energy requirement from Jupiter's mass down to roughly 1,600 pounds of matter converted to energy. That's still an enormous amount of power. We're talking about the complete conversion of mass to energy via E equals mc squared. But it's not impossible. It's not laughable. For the first time, warp drive moved from theoretically possible, but practically ridiculous, to theoretically possible and maybe achievable within a few centuries. That's a huge leap. White had essentially proven that with the right engineering and enough time, humanity might actually build a working warp drive. But White wasn't done. He understood that exotic matter, that mysterious negative energy stuff remained the biggest obstacle. Nobody had ever definitively observed it in nature. It was theoretical, speculative, maybe even impossible. So White started looking at quantum mechanics, specifically something called the Casimir effect. Here's where things get wild. The Casimir effect occurs when you place two uncharged metal plates extremely close together in a vacuum. We're talking nanometers apart. Quantum theory predicts that even empty space isn't truly empty. Virtual particles constantly pop in and out of existence, everywhere, all the time. Between those closely spaced plates, certain wavelengths of virtual particles can't fit, creating a difference in quantum vacuum energy between the inside and outside. This energy difference creates a measurable attractive force, pulling the plates together. Some physicists interpret this force as evidence of negative energy in the quantum vacuum. It's controversial, debated, and not universally accepted, but it's real. The force exists. You can measure it. And in 2021, White published something extraordinary. While studying the Casimir effect for an entirely different project, he'd accidentally discovered tiny warp bubbles forming spontaneously between the plates. Let that sink in. Warp bubbles aren't just mathematical abstractions. They exist in nature, forming naturally at microscopic scales whenever the right conditions occur. This was like discovering fire by accident while trying to invent the wheel. White had stumbled onto proof that warp geometry is real, physical, and achievable. Not with hypothetical exotic matter from some parallel universe, but with actual quantum mechanical effects we can observe and measure right here, right now. DARPA immediately took notice. When the military's Advanced Research Division starts funding your work, you know you're onto something big. They don't waste money on science fiction. They invest in technologies that could actually be built within decades, not centuries. DARPAS involvement signals that serious people with serious resources believe warp drive is achievable. The question is no longer if, but when and how. Eric Lentz's positive energy revolution. While White was exploring quantum vacuum effects, Dr. Eric Lentz at the University of Göttingen approached the problem from a completely different angle. Lentz is younger, part of a new generation of physicists who grew up with warp drive as an established theoretical concept rather than wild speculation, and during the pandemic lockdowns, stuck at home with nothing but time and Einstein's field equations. Lentz made a breakthrough that might be even bigger than White's discovery. Lentz proposed a warp drive that requires no exotic matter whatsoever. Zero negative energy. Just ordinary positive energy arranged in very specific configurations. His design uses what physicists call soliton stable wave structures that maintain their shape while propagating through a medium. Think of them as self-contained bubbles of warped space-time that don't disperse or collapse. They're stable, persistent, and achievable using only conventional physics. The mathematics are complex, but the concept is surprisingly straightforward. Lentz discovered that by layering multiple shells of positive energy density in precise geometric patterns, you can create a stable warp bubble without needing anything exotic or impossible. It's like building an arch, and individual stones can't float in midair, but arrange them correctly and suddenly you've got a structure that supports itself through pure geometry and physics. Lentz's soliton warp drive works on similar principles. Now, before you get too excited, understand that Lentz's design still requires ridiculous amounts of energy. We're talking about power equivalent to a major nation's total energy output over multiple years, all concentrated into a volume smaller than a house. That's beyond anything we can currently generate. And this is crucial, it doesn't require anything we know to be impossible. Future fusion reactors producing gigawatts of continuous power, potentially achievable. Antimatter engines with extraordinary energy density, difficult but theoretically possible. Lentz's design shifts warp drive from needs magic physics to needs really advanced engineering. That's a massive difference. Magic physics might never be achievable. Really advanced engineering, that's just a matter of time and effort. Humanity went from the first powered flight to landing on the moon in 66 years. We went from the first computer to smartphones in roughly the same time frame. Given enough motivation and resources, we solve engineering problems. That's what we do. And if warp drive is purely an engineering challenge rather than a fundamental physics impossibility, then it's achievable. Difficult, expensive, decades or centuries away perhaps, but achievable. The implications are staggering. Within perhaps a century, maybe sooner, if we really commit, humanity could possess functional warp drive technology using only positive energy and conventional physics. No hunting for exotic matter. No figuring out how to stabilize negative energy. Just extremely advanced but theoretically buildable technology based on principles we already understand. Alpha Centauri could be days away instead of millennia. The entire galaxy could open up to exploration. We'd go from cosmic prisoners to free citizens of the universe practically overnight. The EM drive controversy, before warp drive breakthroughs dominated headlines, another propulsion concept briefly captured the world's attention. The M drive, or electromagnetic drive, proposed by British engineer Roger Shore. This device supposedly generated thrust using microwaves bouncing inside a specially shaped copper cavity. No fuel required. No propellant ejected, just microwaves and thrust. It violated conservation of momentum, one of the most fundamental principles in physics, which immediately made it controversial. The concept was simple enough. Trap microwaves inside a tapered, cone-shaped cavity, and the asymmetric geometry would somehow create thrust. Schauer claimed this worked based on relativistic effects and momentum transfer from electromagnetic radiation. Most physicists were immediately skeptical. Conservation of momentum isn't just some suggestion, it's one of the bedrock principles underlying all of physics. Violating it would be like discovering water flows uphill or gravity pushes instead of pulls. Revolutionary, if true, but almost certainly wrong. Yet NASA tested it multiple times, and they reported positive results, tiny amounts of thrust, barely measurable, but not. Then Chinese researchers claimed similar results. Suddenly, the impossible seemed maybe possible. Maybe we'd stumbled onto new physics. Maybe the M drive represented a genuine breakthrough that would revolutionize space travel. The internet exploded with excitement. Forums filled with speculation. Amateur scientists built homemade M drives in their garages. For a brief moment, it seemed like science fiction was becoming reality. Then Dresden happened. Physicists at the Technical University of Dresden decided to settle the question definitively. They built their own M drive, carefully controlled for every possible source of error, and tested it ostensibly. The result? Nothing. Zero thrust. The Dresden team concluded that previous positive results likely came from experimental artifacts, thermal effects, electromagnetic interactions with Earth's magnetic field, measurement errors. When you controlled for everything rigorously, the thrust disappeared completely. NASA never officially commented on Dresden's results. Neither did the Chinese researchers. The M drive quietly faded from headlines, relegated to the dustbin of failed promising ideas alongside cold fusion and perpetual motion machines. It was embarrassing for everyone involved. A reminder that extraordinary claims require extraordinary evidence, and that wishful thinking can sometimes overcome scientific rigor, even among professionals. But here's the interesting part. The M drive's failure actually strengthened the case for warp drive. Why? Because it showed that conservation laws really do matter, that you can't cheat fundamental physics, that genuine breakthroughs require solid theoretical foundations, not just mysterious experimental results. Warp drive, in contrast, has those solid foundations. The mathematics work, the physics check out. It doesn't violate conservation laws. It exploits loopholes in general relativity that Einstein himself acknowledged. That makes warp drive fundamentally more credible than the EM drive ever was. Solitons, nature's warp bubbles. Let's dig deeper into those solitons' lengths discovered, because they're absolutely fascinating and potentially the key to making warp drive practical. In physics, most waves disperse over time. Throw a stone in a pond, and the ripples spread out and eventually disappear. Sound waves in air gradually fade away. Even light can scatter and diffuse under certain conditions. But solitons are different. They're stable wave packets that maintain their shape indefinitely while moving through a medium. Solitons were first observed in water channels in the 1830s. When a Scottish engineer named John Scott Russell noticed a strange wave that maintained its shape while traveling for miles along a canal. This contradicted everything scientists knew about water waves, which normally disperse and flatten out, but Russell had observed something real, a stable, solitary wave, later named a soliton. Since then, physicists have discovered solitons in many different systems: optical fibers, plasma physics, quantum field theory, even cosmology. What makes solitons stable? Essentially, they represent a perfect balance between dispersive forces that want to spread the wave out and nonlinear effects that want to concentrate it. When these effects precisely cancel, you get a self-sustaining structure that neither grows nor shrinks, but simply propagates forward indefinitely. It's like a perfectly balanced, spinning top that never wobbles or falls over. Lentz realized that spacetime itself could support soliton-like structures, stable configurations of warped geometry that don't require exotic matter to maintain. These spacetime solitons would be warp bubbles in the truest sense. Self-contained regions of compressed and expanded space that propagate faster than light while remaining stable and controllable. Unlike Alcubierre's original design requiring impossible materials, Lentz's soliton approach uses only positive energy densities arranged in specific patterns. The beauty of this approach is its elegance. Nature already creates stable wave structures all the time. Water solitons, optical solitons, quantum solitons, they're everywhere once you know how to look. Lentz simply extended this concept to spacetime itself, showing mathematically that general relativity permits soliton solutions that behave exactly like warp bubbles. No magic required, no impossible physics, just geometry, energy, and clever configuration. Of course, creating spacetime solitons large enough to enclose a spacecraft is another matter entirely. The energy requirements remain enormous, far beyond anything we can currently generate. But it's a practical challenge, not a fundamental impossibility. Future technologies, advanced fusion reactors, antimatter engines, vacuum energy extraction might provide the necessary power. And once you can generate enough energy, Lentz's equations tell you exactly how to configure it to create a stable warp bubble. This is why Lentz's work is so important. He transformed warp drive from maybe possible with exotic physics we don't understand to definitely possible with advanced engineering we haven't built yet. That's progress. Real, meaningful progress toward making faster than light travel a reality rather than perpetual fantasy. The path forward, engineering the impossible. So where does all this leave us? We've got White's discovery of natural warp bubbles in the Casimir effect. We've got Lentz's positive energy, soliton solutions. We've got DARPA funding and serious institutional support. Are we on the verge of building a working warp drive? Not exactly, but we're closer than ever before, and the path forward is becoming clearer. The immediate challenge is scaling up. White's Casimir warp bubbles exist at nanometer scales, smaller than bacteria, smaller than cells, smaller than viruses. To enclose a spacecraft, we need bubbles millions of times larger. That requires understanding the fundamental mechanisms behind bubble formation and figuring out how to amplify them. It's like going from observing static electricity to building lightning generators. Possible in principle, extraordinarily difficult in practice. Lentz's approach faces different challenges. We need energy generation capabilities far beyond anything currently available. But energy technology has been advancing steadily for decades. Solar panels get more efficient. Fusion research progresses slowly but steadily. Even speculative technologies like antimatter production and containment are inching forward. Given enough time decades, perhaps a century, we might develop energy sources powerful enough to fuel a Lentz-style warp drive. There's also the control problem. Creating a warp bubble is one thing. Making it go where you want, when you want, safely and reliably, that's something else entirely. We'd need sophisticated understanding of how to manipulate space-time geometry in real time, responding to changing conditions and navigating around obstacles. The engineering challenges are immense, like trying to steer a ship through a hurricane while simultaneously creating the ocean beneath you. But here's the thing, these are all solvable problems. Difficult, yes. Complex, absolutely. But not impossible. not magical, not requiring physics that doesn't exist, just really, really advanced engineering. And humanity has proven remarkably good at solving engineering problems when we're motivated enough. The Manhattan Project went from theoretical physics to working atomic bombs in 3 years. The Apollo program put humans on the moon within a decade of Kennedy's challenge. When we commit resources and talent to a goal, we achieve remarkable things. The question is whether we'll commit to warp drive development with the same intensity we brought to nuclear weapons or lunar landings. Will governments and private industry invest the necessary billions or trillions? Will talented physicists and engineers dedicate their careers to solving these problems? Will humanity collectively decide that becoming an interstellar species is worth the effort and expense? Those are questions we can't answer yet, but the physics says it's possible. The engineering says it's achievable, and the future of human civilization might depend on making it happen. Are we ready for that challenge? Only time will tell. Part 4. Tachyons and Quantum Mysteries Beyond Einstein's Universe. Tachyons, particles that break every rule. What if particles existed that naturally travel faster than light? Not through tricks or warped spacetime, but just by their fundamental nature. Welcome to the bizarre world of tachyons, theoretical particles that make Einstein's speed limit look quaint. The name comes from the Greek word tachys, meaning fast. And these particles aren't just fast, they're impossibly fast, with no upper speed limit whatsoever. Here's where it gets weird. Tachyons supposedly have no interaction with electromagnetic forces. They don't absorb light. They don't emit light. They're essentially invisible to conventional detection methods. How do you measure something with no mass, no fixed speed, and no electromagnetic signature? You can't, at least not with current technology. They're ghost particles, theoretically real, but practically unobservable. Yet particle accelerators like CERN in Geneva have found tantalizing hints. Researchers have detected numerous particles that don't assume stable forms, can't be measured conventionally, and seem to exist in quantum superposition states. The subatomic realm is filled with unstable, unmeasurable particles that appear and disappear in microseconds. Tachyons might be hiding in plain sight among this quantum chaos, unrecognizable because we don't know how to look properly. Think about what this means for reality itself. Our material world, solid, predictable, measurable, might be the exception rather than the rule. At the quantum level, stability is rare. Most fundamental particles are fleeting, unstable, impossible to pin down. We're living on a thin crust of stability floating atop an ocean of quantum uncertainty. That's simultaneously terrifying and exhilarating. Einstein didn't know everything. For a century, Einstein's relativity dominated physics. His equations explained gravity, predicted black holes, described the expanding universe. They were brilliant, elegant, and seemingly complete. But here's the uncomfortable truth. Einstein only saw part of the picture. Just as Newton's laws work perfectly for everyday objects but break down at relativistic speeds, Einstein's theories work beautifully within their domain but fail at the edges. The James Webb Space Telescope is revealing galaxies so old they shouldn't exist, according to our current cosmological models. Hubble found structures so massive they challenge our understanding of how the universe evolved. Radio telescopes have discovered cosmic structures, spanning billions of light years far larger than our theories predicted possible. These aren't minor discrepancies. They're fundamental challenges to our understanding of reality. Our old formulas especially fail when explaining large-scale cosmic structures and the universe's accelerating expansion. Something is missing from our equations. Dark matter and dark energy were invented to patch these holes, but nobody knows what they actually are. We've named our ignorance without understanding it. That's not science. That's placeholder terminology, for we have no idea what's happening. The answer might lie in particle physics, where tachyons, quarks, and other exotic particles operate under completely different rules. Quantum mechanics already breaks conventional physics with its unpredictability and observer-dependent reality. Adding faster-than-light particles into the mix could revolutionize our understanding of everything, or reveal that our entire framework needs rebuilding from the ground up. Tachyons and dark matter, the missing connection. Researchers Samuel Kramer and Ian Redmount analyzed data from Type 1a supernova and found something fascinating. These stellar explosions serve as cosmic measuring sticks, helping astronomers calculate distances and expansion rates across the universe. But the data didn't match predictions. The universe is expanding faster than it should, and the acceleration is increasing. Why? Nobody knows for certain, but tachyons might explain it. Here's the connection. Dark matter makes up roughly 85% of all matter in the universe. Yet, we've never directly detected it. It doesn't interact with light or electromagnetic forces. It's invisible, intangible, detectable only through its gravitational effects on visible matter. Galaxies spin faster than they should based on visible matter alone. Galaxy clusters are held together by more gravity than their stars and gas can provide. Something invisible is adding mass, lots of it. Tachyons have identical properties. They don't interact with electromagnetic forces. They're essentially invisible. Their superluminal speeds could explain why dark matter is so difficult to detect and how it influences gravity without being directly observable. If dark matter is actually composed of tachyons or related faster-than-light particles, it would solve one of cosmology's greatest mysteries while simultaneously revolutionizing particle physics. But are tachyons actually building blocks of dark matter, or do they just exist within it? That question remains unanswered. Either way, their existence would fundamentally change our understanding of the universe's composition and behavior. Breaking causality, time travel's dark side. If tachyons can transmit information faster than light, they could theoretically send messages into the past. That's not speculation, it's a direct consequence of relativity. In Einstein's framework, simultaneity is relative. Events that appear simultaneous to one observer might occur in different orders for observers moving at different speeds. Faster-than-light communication breaks this framework entirely, allowing cause and effect to reverse. Imagine sending a message to yesterday. You could warn yourself about a mistake before making it, or create a paradox where the warning prevents the mistake, eliminating the reason for sending the warning, which means you make the mistake after all. These aren't just philosophical puzzles, they're genuine, logical contradictions that suggest something fundamental about our understanding of time and causality is wrong. The principle of causality states that every effect has a cause preceding it in time. Tachyons could shatter this principle, suggesting that causality might exist across multiple dimensions simultaneously rather than linearly. This fits with another bizarre discovery. Researchers at the South Pole detected mysterious neutrino streams coming from Earth's interior. One explanation: a hidden dimension where time runs backward. Sounds insane, but the data is real and demands explanation. Tachyons aren't just exotic particles. They're potential keys to understanding reality at its deepest level, where time, space, and causality might work completely differently than we've ever imagined. Quantum fields and unstable states. In quantum field theory, Tachyons appear as mathematical solutions representing unstable states. Picture a field trapped in a metastable state, like a ball balanced precariously on a hilltop. Tachyons could trigger transitions to lower, more stable energy states, fundamentally transforming the field's properties. This process, called tachyon condensation, might be how the universe evolves and changes at quantum scales. These unstable states could act as catalysts for dramatic, energetic transitions. When a field falls to lower energy through tachyon interactions, new physical phenomena and states emerge. This isn't just theoretical speculation, it's built into the mathematical structure of quantum field theory. Physicists discovered tachyons not through experiments, but through equations, suggesting their existence might be mathematically necessary for reality to function properly. Here's where it gets truly mind-bending. Tachyons might be related to fundamental symmetries in physics. Symmetries describe how certain physical quantities remain unchanged under transformations. Tachyons could preserve or break these symmetries, making them basic structural elements of physical systems. They might provide keys to understanding symmetry, transformations, and unlocking new insights into the universe's deepest architecture. One particularly fascinating possibility involves supersymmetry, a theoretical extension of the Standard Model, suggesting every known particle has a supersymmetric partner. In this framework, tachyons could appear as supersymmetric partners of ordinary particles, playing crucial roles in symmetry breaking. This breaking could reveal entirely new physical dimensions and phenomena beyond our current theories, fundamentally expanding our understanding of what's possible in our universe and potentially others. Part 5. Traveling at light speed, the human experience. The Doppler effect. Reality bends around you. Imagine accelerating toward light speed in a spacecraft. What would you actually see? The answer is stranger than any science fiction movie. Stars ahead would shift blue as their light compressed, while stars behind shifted red as light stretched. This Doppler effect transforms the cosmos into a surreal tunnel of color. But here's the twist. You wouldn't see stars at all. Astronauts on the moon reported no visible stars in space. Why? In vacuum, without atmosphere to scatter light, only direct photons reach your eyes. The sun's overwhelming brightness drowns out faint starlight. Even traveling between star systems, you'd float in oppressive darkness until approaching your destination. Space isn't the glittering wonderland we imagine. It's an empty void punctuated by isolated points of brilliance. That realization hits hard when you're actually out there. Time dilation, you age slower than everyone else. Einstein's special relativity reveals something profound. Time isn't universal. At high speeds, time slows for the traveler compared to stationary observers. Fly at near light speed for 3 years, and decades might pass on Earth. Your friends age while you remain young. You'd return to a world that moved on without you. This isn't theoretical speculation, it's verified physics. GPS satellites must account for time dilation, or navigation would fail. Particle accelerators observe subatomic particles living longer at high speeds than when stationary. Time genuinely slows for moving objects. Now imagine experiencing this firsthand during interstellar travel. You'd become unstuck from your own timeline, aging at different rates than everyone you've ever known. The psychological impact would be devastating. Returning home to find your children older than you, your spouse elderly or dead, your entire world transformed beyond recognition. That's the hidden cost of relativistic space travel. Physical effects. Your body pays the price. Let's imagine humanity in 2150 finally achieves near light-speed travel. 5 astronauts embark on the first mission. As they accelerate, strange things happen. Their bodies feel compressed, as if sinking into deep sleep while remaining awake. This protective state shields them from psychological stress, but physical effects continue relentlessly. Time dilation makes their bodies appear to shrink and rejuvenate from external perspectives, but internally they suffer. Constant acceleration creates crushing gravitational forces, pressing them into their seats. Muscles atrophy, bones lose density. Their clocks tick faster than Earth's, creating complete temporal disorientation. They can't track how long they've traveled or how much time passed back home. Eventually, they reach a distant solar system. If they survive the ordeal, they make groundbreaking discoveries, but returning home reveals the horrifying truth. While only years passed for them, decades elapsed on Earth. Everyone they knew aged dramatically or died. Their sacrifice enabled humanity's reach into the cosmos, but at devastating personal cost. This stark reality shows why faster-than-light travel isn't just desirable, it's necessary for preserving human connection across the stars. Teleportation, beaming through space. Science fiction promises teleportation as the ultimate travel solution. Imagine disintegrating at one location and reconstructing at another instantly. Star Trek's transporter made this seem plausible, even routine. But could it actually work? Quantum mechanics suggests theoretically yes, matter can be reduced to information, transmitted and reconstructed elsewhere. The mathematics exist. However, challenges are staggering. Replicating a human at the atomic level requires capturing and transmitting incomprehensible amounts of data. Every atom's position, every electron's quantum state, every molecular bond all perfectly recorded and reproduced. One error means death, or worse, incomplete reconstruction, creating something horrifying. Then there's the philosophical nightmare. Are you actually transported, or does the original you die while a perfect copy awakens elsewhere? Does consciousness transfer, or does a new consciousness emerge, believing it's you? These aren't just thought experiments, they're fundamental questions about identity and existence that teleportation forces us to confront. Until we answer them, beaming remains firmly in fantasy territory. Photon propulsion, riding laser beams to the stars. While warp drive remains decades away, physicist Philip Lubin offers a nearer-term solution: photon propulsion. Imagine massive Earth-orbiting lightweights propelling lightweight spacecraft using pure light. The craft carries enormous reflective sails catching laser photons, converting light pressure into acceleration. No fuel required, just photons transferring momentum. Lubin's calculations show unmanned probes could reach 25% light speed, roughly 46,000 miles per second. That's Alpha Centauri in just 20 years instead of millennia. Larger crewed vessels would travel slower, perhaps reaching 380 miles per second, but still dramatically faster than current chemical rockets. The technology exists today in principle, we just need the engineering scale-up. The system requires powerful laser arrays circling Earth, coordinated perfectly to focus on distant spacecraft. The sail must be enormous, yet incredibly lightweight, reflecting most incoming photons while absorbing minimal heat. Control systems must handle real-time adjustments as the spacecraft accelerates. It's challenging but achievable with current physics and near-future engineering. Photon propulsion might be our stepping stone to the stars, bridging the gap between today's chemical rockets and tomorrow's warp drives. The future isn't just coming, it's racing toward us on beams of light. Light's true nature: does speed even exist? Here's something that'll blow your mind. At light speed, time stops completely. For a photon traveling from a distant star to your eye, no time passes whatsoever. From the photon's perspective, it's created and absorbed instantaneously. Even if observers see it traveling for billions of years. Time and distance are observer illusions. Photons experience neither. This raises profound questions. Does light actually have speed? Or does our limited perception create that impression? Quantum physics shows light behaves impossibly, existing as both particle and wave, appearing in multiple places simultaneously, affecting outcomes through observation alone. Light isn't the simple phenomenon we imagine. It's deeply strange, fundamentally mysterious, potentially the key to understanding reality's true nature. Recent experiments at Imperial College London slowed light dramatically from 186,000 miles per second down to just 66 feet per second. Think about that. Light, the universe's speed limit, reduced to slower than a car on a highway. If we can manipulate light's speed this drastically, what else becomes possible? Could we create light gates where time and space behave differently? Could we literally step through light and emerge elsewhere? These aren't just science fiction fantasies anymore. They're emerging research frontiers that might revolutionize everything we understand about transportation, communication, and reality itself. The universe's secrets are hidden in light, and we're finally learning to read them. And that's why, every evening as darkness falls, we're actually embracing the universe's deepest secret. Light, this mysterious, incomprehensible entity that is both wave and particle, isn't just a tool that allows us to see. It's a window opened in the fabric of time and space. Scientists at Imperial College have shown they can bend light within time itself. Perhaps tomorrow we'll completely decode the language of light. Perhaps we'll finally understand that the universe is actually much softer, much more flexible, much more mysterious than we imagined. Tonight, as you lie down in your bed, think about this. Even in that darkness, when you close your eyes, billions of photons are still continuing their dance. They're reflecting from your walls, from your blanket, from your skin. In this silent ocean of light surrounding you, you're witnessing all the miracles of the quantum realm. As you drift into sleep, let this be your final thought. Perhaps your dreams are taking place in another dimension of light we haven't yet discovered. Perhaps every morning when you wake up, you're not just opening your eyes, you're returning to the reality that light has chosen to show you. Good night, sweet dreams. And remember, when the sun rises tomorrow morning, it won't just be a new day beginning. The universe's oldest and most mysterious messenger, light that left the sun 8 minutes ago, will knock on your window to say hello to you again. Sleep in its embrace tonight. You are safe.